Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the second video in a series on the definite integral. The first video was just a review of some very important summation properties that you need for integral calculus. At this point, we're now going to step into integral calculus with the definition of the definite integral. And it requires us to recall something that we've been doing recently up to this point. And I'm not talking about derivatives. Now, I've taken a little bit of break between recording video sessions, and so it's been a while since I have actually talked about this topic. When I say a while, it might have been 3 or 4 days, but still, that's a while for me. So I just think it's a good idea to review this anyway. We've been talking about dicing up an interval from x equals a to x equals b into n sub-slices. These sub-slices we were calling sub-intervals. And the whole point of doing this was to help us find the area underneath a curve. And when I say underneath, I mean really between the function itself, this blue curve, and the x-axis, which is this horizontal line right here. And we called each of our slices by names. For example, this would be our first slice. Here's our second slice. Here's our third slice, and so on and so forth down the line. Now remember, we had n of these sub-intervals, so this last slice would be my nth slice, and the slice right before that would be my n minus first slice, and this would be my n minus second slice, and so on and so forth. And then somewhere in the middle, we had an arbitrary slice, which we'll just call the ith slice. And that ith slice is the most important of the slices because it's arbitrary. It's just the one that we're going to do that represents all slices. All of these slices, at least in Calc 2, are going to be of the same width. So we're going to assume that the slice size is always the same. And since we have cut this interval into n sub-intervals, the average width, or I should say just the width of each slice, we will call delta x, and that is the distance between the end, the right end point of this interval, and the left end point of this interval, divided by n. So we're just cutting up this interval into n sub-intervals. And again, each of these has a width of delta x. Every single one of them has that very same width. Up to this point, that's what we've been doing. There are a couple other things I need to mention here. I'm going to erase that delta x because it's going to get in my way. And the things that I want to mention are how we labeled the edge points of each sub-interval. It all starts with the leftmost edge point of our intervals here. A is defined to be x sub 0. It's our 0th point. Even though this interval here is the first interval, the left edge of it is called the 0th point. And then this will be x sub 1, this will be x sub 2, this will be x sub 3. Notice the third interval has a right edge, or the third slice has a right edge of x sub 3, the second slice has a right edge of x sub 2, and the first slice has a right edge of x sub 1. Using that same pattern, we can easily see that the nth slice should end at x sub n. And therefore, the n minus first slice should end at x sub n minus 1, and the n minus second slice should end at x sub n minus 2. And the all-important ith slice should end at x sub I, which means its left edge is x sub I minus 1. That will be important. So again, we've talked about all this stuff up to this point, but it's a nice review, right? Now we would love an algebraic way to arrive at, let's say, the 17th x value. Rather than counting, let's say our interval went from 0 to 1,000 or something like that, and we diced it into 60 pieces. Rather than counting, well, x sub 0 is 0, x sub 1 is 60, or whatever. We diced it into 60, so it's not 60, but 1,000 divided by 60. X sub 2 is 2 sets of those thousands divided by 60, and so on and so forth. It might be nicer just to quickly arrive at the 17th slice with a formula. And the formula to arrive at the ith slice is the following. X sub I is A plus I delta X. So that is, let me just give you an example. If we looked at X sub 0, we'd start at A and we would not move at all. So in other words, we'd be at A, which is exactly true right there. If we wanted to get to X sub 1, we'd start at A and we'd take one step of size delta X. That is true. Start at A, take one step of size delta X to get to X sub 1. If you want to get to X sub 2, again, you start at A and you take 2 step sizes of size, or steps of size delta X. So 2 steps of size delta X will give me to X sub 2. And so on and so forth down the line. So that is the justification for the formula. X sub I is equal to A plus I delta X. Those two formulas you will have to commit to memory. They're very, very important. Again, we've already derived this, but it's just nice to review it. At this point, we had everything set up to start saying, well, let's go ahead and approximate the area underneath this curve. And to do that, we just created rectangles. So if you take a look at each of these slices, they can be made into rectangles by choosing an appropriate sample point in each interval. For example, let's pretend for a moment that we chose to use the following. Let me go ahead and use a different color other than green or red or blue. Let me use this annoying looking color. So let's pretend as though we chose a value right here. It's not the midpoint or anything like that, but we'll just call it X sub 1. In other words, it's some value, but I'm going to call it X sub 1 star. In other words, it's some weird kind of sample point between X sub 0 and X sub 1, but it's not necessarily X sub 1, nor is it necessarily X sub 0. It's just some sample point in that interval. So I should say X sub 1 star is just a sample point in the interval X0 to X1. And what we're going to do is evaluate the function at X sub 1 star. So if you take a look at that point is X sub 1, star, whatever that sample point is, f of X sub 1 star. That's supposed to be an X there, sorry about that. So that's the point, which means the height, if I put a cap on top of this to make a rectangle, the height of that rectangle would be f of X sub 1 star. Now, obviously, we don't have to choose a random point within an interval. We could have chosen a middle point, or the right edge point, or the left edge point. In most cases, we like to use right endpoints just because it simplifies the mathematics quite a bit, but you don't have to. All right. So for this recall, let's just pretend as though we're choosing the right edge point of each interval instead of some random point, arbitrary point in there, but we'll just choose a right edge point to give us the height of each given rectangle. If we do that, the right edge point of the first interval is right there, and it's based upon the point X sub 1 comma f of X sub 1, which makes the math a lot easier because then we can say the height of the first rectangle there is f of X sub 1, and the height of the second rectangle is f of X sub 2, and the height of the third rectangle is f of X sub 3, and in general, the height of the ith rectangle is f of X sub I. And all we want to do is add up all those areas. So I can say, well, the area underneath this curve is approximately the area of the first rectangle plus the area of the second rectangle plus all the way down until you get to the area of the nth rectangle. And that is going to equal a sum of areas. I'll just say I equals 1 to n of a sub I. But the area of each rectangle is its height times its width. And because I wrote the index I there, my sample is going to be the ith rectangle. That's why the ith rectangle is so important. So let's see, this is going to be the summation. I equals 1 to n. The height of that rectangle is f at x sub I. That's the height right there. F at x sub I. So we're going to go ahead and write that down. F of x sub I. And then its width, just like all the other rectangles, is delta x. And that was called a Riemann sum. So again, just to remind you of everything we've done. I know it's a long-winded reminder, but it's very important that we have a very solid foundation. By the way, you cannot get away from this derivation in Calc 2 because you're going to use it in 3 dimensions and you're going to continually use this. You're going to slice things up like this all the time. The only other thing I want to say here is that really that's an approximation for the area, but we know that if we take those slices smaller and smaller and we include more slices, so instead of 10 slices, we go to 1,000 slices or 1,000,000 slices, basically we allow the number of slices to go to infinity, then we will get a much better approximation for the area underneath the curve. And as n goes to infinity, we'll get the actual area underneath the curve. And folks, that is the definite integral. Everything in this definition is what we've just re-derived. Let f be a function that exists on the closed interval from a to b, where this interval has been divided into n subintervals, there you go, each having a width of delta x sub I. Now, I wrote delta x sub I there, but really, in our differential calculus and actually integral calculus, all those widths are going to be equal. So it's just going to be a delta x. So you can ignore the sub I there. We're going to let a equal x naught. And then we have x1, x2, x3, all the way to xn, which is b. And those are the endpoints of all the sub intervals, which we've already seen in our previous picture over here. The first interval has endpoints x naught and x1. The second interval has endpoints x1, x2, and so on and so forth. All right, let's see what else we have going on in this definition. We'll let x sub I, or sorry, x sub 1 star all the way to x sub n star be sample points in each of these subintervals. And that's what I was saying earlier with x sub 1 star. It didn't have to be a right endpoint. It didn't have to be a left endpoint. It doesn't have to be a midpoint. It just has to be a point in the relative or in the relevant, interval. So x sub 2 star should exist between x sub 1 and x sub 2, and it can actually be x sub 1 and x sub 2. Generally speaking, if you're going to use a left endpoint, then let me mark it right here. You would use this for left endpoints. I'll just put EP for endpoint. And you would use x sub I, and let me use red because for some reason I like red for right and green for left. X sub I would be used if you're using right endpoints. Okay. And then their average is what you'd use for the midpoint. Then, here goes the definition. The definite integral of our function from a to b is defined to be this weird looking notation that you've likely seen over and over again for quite some time but never used. But this notation right here, this sign that looks like an elongated S, is called the integration sign. And that notation is equivalent to saying we're going to let n go to infinity of our Riemann sum. In other words, we're going to have an infinite number of slices. Now, I have always found that this limit notation is much easier to understand than the next one I'm about to show you. But, I've dealt with mathematics long enough that I totally understand it, but I remember when I was a student, I was a little bit confused about the following notation. So this one should be okay. I'm just slicing up, instead of 10 slices, I do an infinite number of slices. Now, I hope you would agree that the more slices we have, the thinner each of those individual slices gets, which means that the more slices we have, the smaller your thickness of each slice, delta x, is going to be. And that's exactly what this other version is we could say, instead of saying the number of slices are going to infinity, we're going to say that the thickness of each slice is going to 0. Now, you'll have to forgive my very theoretical notation there. That limit is actually more true than what most textbooks are going to say. That limit is saying that if you're varying the thickness of each of your slices, well, we're going to let the maximum thickness tend to 0. Don't worry about that. Basically, we're just saying let delta x go to 0. Okay, so the thickness of each of our slices goes to 0 means we have more slices. So each of these two limits are saying the same thing. So anyhow, that is actually that Riemann sum. The limit of the Riemann sum is actually defined to be the definite integral, provided that limit exists, which more often than not it does. If it does exist, we say that our function is integrable. That's hard for me to say, but that is what it means. So our function is integrable on the closed interval from a to b. This a right here is called the lower limit, and b is called the upper limit. So you have a lower and an upper limit for your integral, and they're also known as the limits of integration. All right. So that is the actual true definition of a definite integral. Now that we know that actually, and we know that it's nothing really magical, all it is a Riemann sum, and we're just allowing n to go to infinity, we can now start Calc 2. Let's start with a very simple example. Set up but do not evaluate a definite integral that represents the limit on the interval -1 to 15. So somebody's walked in the room and they've said, hey, here is a limit as n goes to infinity of a Riemann sum. Really, this, if you take a look at this highlighted piece right here, I can call that f of x sub I. And so in reality, somebody's just saying, what is the limit? What's a better way to write the limit as n goes to infinity of the summation I equals 1 to n of f of x sub I times delta x? Well, I already know what a better way to write that is because I've just read the definition. It's going to be an integral. We're summing up, and watch how this works. It's going to be the sum of, or the integral of, f of x dx. Notice there's a lot of similarity. F of x sub I versus f of x. And when you have your slices, your delta x's go infinitesimally thin because you're allowing more and more slices, so your slices get thinner and thinner, that delta becomes a d. So instead of a delta x, we have a dx. And we were told, which they kind of have to tell us, at least in a problem like this, that the limits of our integration are going to be from -1 to 15. That is, our integral is going to go from a -1 to a 15. Let me just tell you, really what that means is we're going from x equals a -1 to x equals 15. Most people would not write the x equals there, and I don't blame you if you don't, that's fine. However, it will become important as you move forward in Calc 2, actually in Calc 1 as well. Now, we're not quite done with this because I didn't quite write this the way I'm sure that most people would want you to. So I'm going to say that this is equal to the integral from -1 to 15. And instead of writing f of x, I'll just write e to the x. Notice I'm just replacing the x sub i's with x's. So e raised to the x plus tan inverse of x. Write that in there. Tan inverse of x. And then minus 3x squared. And I put parentheses on this just out of habit, dx. So I'm integrating that group of functions with respect to x. Actually, that dx means, honestly, when you read this, it means with respect to x. As you move forward in calculus, you will be able to integrate multivariate functions. So functions involve x, y's, and z's with respect to different variables. So that's why we need to be very clear to the world. We are integrating this with respect to x. Now, right now, I'm not asking you to integrate this. I'm just asking you to set this up. That's it. So we just want to use the definition to transform between the limit of a Riemann sum into a definite integral. That's a skill that you'll need to have. Now, to be honest with you, that first example was kind of a softball because we're just starting into transforming from limits of Riemann sums into definite integrals. However, this is much more typical here. So somebody gives you this L sub n is equal to 2 over n summation I equals 1 to n of this stuff right here. It's a bit of a mess, right? And they say, well, we want to take the limit as n goes to infinity, and we want you to express that as a definite integral. And I just realized right as I was writing this, that should be an r sub n just to imply that we're dealing with right endpoints. That was my typo. Sorry about that. So given that r sub n is equal to that summation, we want to take the limit as n goes to infinity of r sub n, which is the limit as n goes to infinity of, well, that stuff they've handed us. Now this is going to take a little bit of detective work on your end. In the previous problem, they just gave us the fact that our functions, if you take a look over here, were e to the x sub I, tan inverse of x sub I, 3 times x sub I squared. But in the problem that we're working with right now, there's definitely no x sub I. You can't see the x sub I. They've hidden it from us. But there's some structure going on here to imply what the actual function is. So let's take a look at the pieces which imply what the function is. Whenever I see some type of pattern within an expression in a Riemann sum, specifically that pattern right there, 3 plus 2i over n, I immediately think that must be x sub I. So I'm going to write that down below. I'm going to say x sub I looks to be 3 plus 2i over n. Now remember, there's two very important formulas for us to be working with. They are the following. Delta x is supposed to be b minus a over n, and x sub I is supposed to be a plus I delta x. Well, if x sub I is supposed to be a plus I times the delta x, take a look at this. This must be right here, a. Let me go ahead and rewrite this slightly here. This is 3 plus I times 2 over n. Now you can probably see it much better. That must be a, where we begin our integral. And this piece right here must be our average width of our slices, right? Delta x. So we know in this case, a is 3 and delta x is 2 over n. But remember, delta x is supposed to be b minus a over n. Well, we know what a is. We know a is 3. We can see it just right here. Remember, I'm looking for that pattern of something plus something with i's. There we see it, and I just wrote it. That x sub I must be that 3 plus 2i over n, which means x sub I is 3 plus I times 2 over n. That is, our integral starts at a equals 3 and our delta x is 2 over n. So if I know that delta x is 2 over n, and I know that a is 3, well, the only way that I can get this to be a number 2 over n is if b is equal to 5. So this is why I know b is equal to 5. I know where our integral ends. Our definite integral starts at 3, and our definite integral ends at 5. That's very, very important. So really, now I can kind of rewrite this. Maybe I'll do it like this. I can rewrite this as the limit as n goes to infinity. I'm going to not write that 2 over n yet because I want you to see something. Of the summation I equals 1 to n of the quantity 2x sub I squared minus 7x sub I to the 5th times 2 over n, which by the way is our delta x. So that's what I did with that 2 over n is I grabbed it and I moved it on the inside, just parked it right there. But remember, 2 over n is delta x. So that's why I wrote delta x off the back end. And now you can see this gets traded out for, since it's a limit of a Riemann sum, the definite integral starting at a, which we said was 3, ending at b, which we said was 5, 2x squared minus 7x to the 5th dx. I'm really stealing all my notation from here. This is our function evaluated at x sub I. There we go. That is a good kind of robust problem. A lot of students have a hard time initially seeing the patterns. I'm really trying to drive that home though. Look for common statements. Even if, let's say that somebody didn't hand you the back end of this. Let's just say that this was gone. Okay. Let's just say they handed you only this piece of it right here. Well, the pattern, there's not much of a pattern, but you can see you have 3 plus 2i over n. So I'm going to pretend as though that's my x sub I. And then I can now do what I just did. I can't just say, oh, that's x sub I, so it's 2x squared. I need to know the limits of the integral, of the definite integral. And so that's why I wrote down all this information right here. Well, x sub I is 3 plus 2i over n, or 3 plus I times 2 over n, because that 3 tells me where my definite integral starts, and then I use that information to help me find out where my integral ends. Anyhow, so that is transforming from the limit of a Riemann sum into a definite integral. The final example is actually a lot easier. When somebody hands me a definite integral, transforming that into a Riemann sum, or the limit of a Riemann sum, is pretty easy. You just have to remember, again, those two formulas. You have to remember that delta x is defined to be b minus a over n. In this case, b is 10, a is 1. So this is going to be 9 over n. And then x sub I is defined to be a plus I delta x. In this case, a is 1 plus I, and we've just computed that delta x is 9 over n. So if I want to rewrite this statement as the limit of a Riemann sum, I will say, well, that's the limit as the number of slices goes towards infinity of the Riemann sum. And the Riemann sum is I equals 1 to n of f of x sub I, I'll just write it that way, f of x sub I times delta x. But now I can't leave it just like that because I know what x sub I is. I just computed it over here. So let me go ahead and insert all those values in. This is going to be equal to the limit as n tends to infinity of the summation I equals 1 to n of f evaluated at x sub I, which we said is 1 plus 9i over n. 1 plus 9i over n delta x, which was 9 over n. Again, you're not quite done with this because we really need to write it in this function here. So let's go ahead and do that last little bit. I'm going to take that function, which is x minus 4 natural log of x, and I'm going to evaluate it, or at least plug in. I'm not going to actually evaluate it though, but I'm going to plug in 1 plus 9i over n. So I equals 1 to n of, let's see, x, which is just 1 plus 9i over n, minus 4, the natural log of that 1 plus 9i over n. And then don't forget, times 9 over n. All right. That's the Riemann sum, the limit of the Riemann sum, that is equivalent to the definite integral from 1 to 10. Definite integral is definitely, pun intended, easier to write, and that's why we like to work with definite integrals. They're much easier to write than this limit of a Riemann sum. And as we move forward, we'll begin to evaluate them really, really quickly. That's it for this video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles. obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.